Well, cool. Yeah, so welcome back. Um, so just like last time, I am going to be recording this video or I'm going to be recording this class and posting it as a video up to YouTube. So anybody who was unable to actually attend the class can, you know, watch along and can stay abreast in what we're talking about in the class. At the same time, you can find it there if you want to revisit anything that we talked about today. And so the stuff that we're talking about today is the continuation of, or I should say is the next step in series. We were talking about activity sheet 17, or you were asked to look at activity sheet 17 last time. And activity sheet 17 continues to look at series. I'm going to grab my pen here. So it continues to look at series, continues to look at these objects of the form, right? They're sort of like formally written like this as a giant sum, as an index is allowed to go from some number. It could be 0, it could be 1, it could be 8. Let's just say from 1 to infinity of numbers of the form a sub k, right? And this is thought of as an infinite sum, a1 plus a2 plus a3 plus ... So what we're looking at, or what you were asked to look at for today's class, are sequences where all of the, or series where all of the a sub n's were positive. So we're only looking at series where, for now, right, for now, a sub n is bigger than or equal to 0. Every a sub n is bigger than or equal to 0. So all of these numbers that we're looking at are positive numbers. And what we saw in the lead up to today's class is that there are a number of things that we can do with these series as far as determining whether or not they converge to a number, right? Whether or not we can make meaning of this infinite summation. And so the big things that we saw included the integral test for convergence, the comparison test for convergence. We also saw the limit comparison test for convergence. And we're talking about a special kind of series as well, known as a p-series, right? So we defined what a p-series is. We'll revisit that today. Just as a way to kick things off, one of the big surprising things that we saw in the set of videos leading up to this class is that not every sequence, or I should say not every series whose individual terms go to 0, not every series that looks like that actually converges, right? I think this was surprising, at least for me personally. This is super surprising. So if you take two different series, so if you took like the sum as k goes from, let's say, 0 to infinity of expressions of the form 1 over 2 to the k, right? Or if I want, I can write that as 1/2 to the k, right? And I compare that series to the sum as, let's just say, k goes from 1 to infinity of 1 over k, right? The series on the left looks like 1/2 plus a 4th plus an 8th plus ... While the series on the right looks like 1 plus a 1/2 plus a 1/3 plus a 4th plus ... So both of these, in some sense, they look kind of similar. They both have terms that are fractions that are decreasing, right? These fractions are always of the form 1 over something, and that something is getting smaller and smaller and smaller, right? That's true in this case, and that's also true in this case. But the one on the left, we saw definitively converges, right? So that's a geometric series. So that's a geometric series, and it converges to the expression, the formula for a geometric series was that it converged to the expression c divided by 1 minus r, where c was the first term, right? So c was that first term, that's a 1/2, and r was what you had to do to get from one term to the next, right? Whatever that common ratio was. So in this case, multiplying from 1/2 to 1/4, 1/4 to 1/8, that was also 1/2. And so we ended up getting that in this case, the geometric series converged to 1/2 divided by 1 minus 1/2. That's 1/2 over 1/2, so that's just equal to 1. So it turns out that this geometric series converges to 1. Something that we saw, I think, in not even last class, but the videos before last class. So this particular geometric series converges, and it converges to 1. At the same time, we saw in our video that this harmonic series actually diverges, right? It's very, very slow to do so, but it diverges all the way to infinity. And so even though these two series look kind of similar, and the individual terms are getting smaller and smaller and smaller, right? Like 1/4, 1/8, these terms will go to 0. Over here, 1/2, 1/3, 1/4, those terms will go to 0. The individual terms go to 0, yet the overall infinite summation has very, very different behavior, converging to just a finite number and a small finite number versus diverging to infinity. So number one, super surprising. Number two, super unfortunate, because it means that determining whether or not a sequence converges or diverges is actually super challenging. It's hard to just look at a sequence and determine whether it converges or diverges. So that's some of our goals for today, and that's some of these tests for convergence. So the integral test, the comparison, and limit comparison tests. These are things you saw in the videos, and these are here to try to help us better understand when a sequence converges and when it diverges. So I'm going to turn the slide here in a moment. Let me pause for a second because I've been talking at you kind of nonstop. I'm going to take a sip of coffee. I'm going to pause. Let me know if there are any questions. Feel free to jump in or to say something in the chat or anything like that.
Can I ask you a question about the homework?
I'm happy to talk about the, is this a general question or a specific question?
A specific question, not a problem.
So I don't want to talk about that right now in class. This would be the homework that was due last night. That was about differential equations, just a completely different topic. I'm happy to talk about that, but I'd prefer not to use class time to do that. Let's check in either immediately after class or during office hours. Yeah, super happy to talk about it, just not right this moment.
Okay, sounds good.
Awesome, awesome, awesome. Yeah, any other questions? All right, cool. Well, let's keep going. Getting a little better at this user interface. So let's jump over here. Okay, so I want to talk through our sort of framework for the integral test. This was something that we talked about in the abstract in the videos, but I want to actually use it to look at a series. And we're just going to look at our friend, the harmonic series here, which we already know diverges. So we sort of know what we're aiming for. So the harmonic series, right, that was the series right here. And we know that this diverges, but according to the integral test, we can see that this diverges by comparing it to an infinite integral, right? Or an improper integral. So instead of just adding up these individual values, 1/2 plus 1/3 plus 1/4 plus et cetera, I can consider the entire improper integral where I'm converting my 1 over n to an expression 1 over x, and then I'm going to integrate from 1 up to infinity in this case. And so if I want to compare these, right, I actually have a really nice means for doing so. Let me draw a quick set of axes down here. We'll see how good I am at drawing a picture relatively quickly. So if I have this as my set of axes and I have the function f of x equals 1 over x, and we'll pretend that this is nice and smooth. And it kind of looks like that. That's not so bad. Okay, so if that's our function, f of x equals 1 over x, and if I wanted to actually consider the relationship between this function and the corresponding sequence, note that, let's see here. So let's see, so this is the number 1, let's say 2, 3, 4, and so on, that I could represent, first of all, this object, the integral from 1 to infinity of 1 over x dx. I could represent that as this sort of infinite area here, right? So that's going to be all of this area sort of stretching off to infinity. So all of that red area. At the same time, if I wanted to try to visualize this expression, this infinite sequence, or this infinite series, I could think about, well, the first term, right, is just the number 1. And I can visualize that by noting, and here's where my axes are going to sort of fail me here, but if that was the number 1 down there in red, then this should be a height of 1. Right, so that should be a height of 1. This should actually be a height of 1/2. So pretend this is drawn well and to scale. You know, just like in class, pretend I've got a good picture going here. This point, oh man, this is getting a little rough. This would actually be 1/3. This number here would actually be 1/4, and so on. And so if I wanted to visualize this infinite series, I could imagine that adding the number 1, that's like adding this blue box, right? This blue box has a width of 1, it has a height of 1, and so the number 1 could be represented geometrically or visually as this, what should be a square, right, of height 1 and width 1. The next number in the series, 1/2, can be represented with this box, right? So that, again, that has width 1, that has height, supposed to be 1/2. And so 1/2 times 1, the area of that box is equal to 1/2. This next one has an area equal to 1/3. Again, the width is 1, the height is 1/3. And so that box right there has an area of 1/3. And this next box, we could think of it as having an area of 1/4. Again, width 1, height 1/4, and so on and so on, right? So for each of these boxes, right, for this box, the area is equal to 1. For this box, the area is equal to 1/2. Here, the area is equal to 1/3. Here, the area is equal to 1/4. And so we actually get this really fantastic direct comparison between the infinite integral, right, the improper integral, which is sort of written here and is drawn in red, and then this infinite series, which is drawn in blue and is going to be the area of each of these boxes added up and added up, right? And so if I were to draw the area represented by the series in blue, it would actually be an overestimate of the improper integral, right? Because it would contain all of this, plus all of this, plus all of this, and plus all of this, and so on, right? And so in each time we add up the next term in our series, we're getting this overestimate. So we're getting this extra piece right here, and this extra piece right here, right? And so what we see then is that in this case, if I were to take this as my blue area, represented as area, and then this other thing, this improper integral, as my red area, then I'm really getting that the red area is strictly less than the blue area. And so I get this really fantastic direct comparison between the two. And so instead of actually dealing with this infinite series, I can instead try to integrate this infinite integral right here. And what we see is that that infinite integral actually integrates to become, right, sort of a quick review of improper integration. That would go from 1. So we can't integrate directly to infinity, right? But we can integrate from 1 to b, and then we can take a limit as b goes to infinity. So that ends up looking like this. This ends up becoming, right, again, the limit as b goes to infinity. The 1 over x becomes an ln of x, and so that looks like ln of x evaluated from 1 to b. So that's like the limit as b goes to infinity of ln of b minus ln of 1. ln of 1 is just going to be 0. ln of b, as b goes to infinity, just gets bigger and bigger and bigger. And so this entire thing actually diverges to infinity. And so what we can conclude then is that this improper integral, right, the red area, is infinite. There's infinite amount of red area under there. And so therefore, since the series can be represented visually as actually having more area than the red area, that will also necessarily diverge. So this is a second argument that the harmonic series diverges. But this is an argument that really sort of exemplifies the integral test, where instead of looking at this expression, I can instead look at a improper integral and take that as my integration. Yeah, so we'll end up, I should say, when we use this in practice, we won't have to always draw this picture and go through this song and dance. Oftentimes, what we're really doing is a move that takes, you know, sort of this object, this integral, this series, and allows us to directly just sort of jump over and consider this object. And so that's really helpful, especially if we have a series that we know how to integrate. I'm going to change the slide here in a second, and that means I'm going to have to erase these beautiful drawings. So maybe I'll pause here again. Let me know how it's going so far, and any questions about what we've drawn up here. All right. If there are no questions at the moment, let's jump over to the next slide. Bam. Oh, okay. There we go. Great. I go too far? No. Okay. So I'm going to skip ahead for a moment and talk through problem 4, right? I think I probably ordered this slightly, not incorrectly, but I think I could have ordered this better by putting problem 4 immediately after problem 1. Problem 1 looks at another expression. Instead of looking at the expression 1 over x, it's asking us to look at the expression, there we go, to look at the expression for the infinite series of 1 over, let's say, n squared. Sum as n goes from 1 to infinity. Now, again, this is one that we actually know converges, right? This series converges. We don't necessarily know what it converges to, but we know that this converges, and we know this because it is a p-series, right? A p-series was something of the form sum as n goes from 1 to infinity of 1 over n to the p. Oops, 1 over n to the p. And so this is a p-series with p equal to 2. And we saw that p-series will always converge if our p-value is strictly bigger than 1. So in this case, p equals 2, strictly bigger than 1. This is going to converge. Let's take a look at the integral test and see how the integral test allows us to draw the same conclusion. Right, so here's our, sorry, I keep skipping slides accidentally. Here is a picture of the function 1 over x squared. You can see I didn't actually trust myself to draw this freehand, so I imported a picture. And notice we have a similar setup as before. I'm comparing what is in blue, the series, 1 over n squared, to what I could nicely write in red as the integral from 1 to infinity of 1 over x squared. Right, so the shaded area in the picture, that's corresponding to our series, right? We have these rectangular boxes. The integral in red would really be this area here. So it'd be all of this area under the integral sign, sort of going on infinitely. So yeah, all that good area there. Okay, so if that's our area, and I want to be able to draw a direct comparison to the integral itself versus the series, I'm still getting the same picture as I did last time, which is that whatever my integral area is, that is going to be strictly less than the blue area, which is unfortunate. Right? Because what I'm ultimately going to do here, to get a little bit ahead of myself, is I'm going to integrate this, see that it's a finite number, see that it converges, and try to use that to draw a conclusion about whether or not this converges. So what I would really love to have, right? What I would really love to have is an inequality that looks like this, an inequality that says that the red area is bigger than the blue area. If that were the case, then having the red area be finite would mean that the blue area is finite. Unfortunately, that's not the case as written, right? Or as drawn. As drawn, the red area is less than the blue area. And so even if the red area is finite, that's no guarantee that the blue area is also finite. So in that case, we're actually in a little bit of trouble, but we have this really clever sort of geometric maneuver that we can do. All right, so let's take a look and do this, this geometric maneuver. So the geometric maneuver is this. I'm going to go back to my picture. I'm going to draw in blue here. And all I'm going to do is I'm going to take each of these rectangles and shift them 1 unit to the left. Right, I'm going to shift them 1 unit to the left. So this rectangle gets moved over here. Now here I don't have a pre-rendered picture, so you're stuck with my drawing. This rectangle gets shifted to the left. The next rectangle gets shifted to the left. The next one gets shifted to the left, and so on. Every single rectangle just takes a single step to the left, right? And to just make sure it's clear what I'm doing, so this original gray rectangle took a step to the left and became this rectangle right here, right? And similarly, this rectangle took a step and became that skinny rectangle there. And so now take a look at what we have. By having every single rectangle just take 1 step to the left, I have this first rectangle, which is fine. That's just floating off there by itself. But for every other rectangle, I now have that the rectangle is lying directly under my curve, right? So my blue rectangle, for example, I'll pick on this one. This blue rectangle is actually lying under that portion of the curve that I have. And so that means that my integral is actually creating an my integral is creating an overestimate, right? My series is lying under my integral. So if I were to draw this when compared to my red area, look at all of this excess red area, right? The red area covers all of that as an excess, all of that as an excess, and so on. And so I actually can get the inequality that I'm looking for, where my red area is actually sitting over, I'll do this in purple, my red area is sitting above my blue area, with the exception, put a little asterisk here, right? And the asterisk is with the exception of the first rectangle. with the exception of rectangle 1. Right? But that's okay. And so now the idea is as follows. We can calculate our integral. We'll see that the integral is finite. That will mean that the series, with the exception of that first rectangle, that first term, but the rest of the series is also finite, right? It's going to be less than a finite number. And then because this is finite except for rectangle 1, I can just throw rectangle 1 back into it. That's like adding on one additional number. And so if the original was finite without rectangle 1, then the whole series with rectangle 1 should also be finite. All right, and so that's going to be our idea here. Moving, yeah, see, unfortunately, I cannot save these pictures as I move from slide to slide. It's one of the big failings of this program, I think. But so we've shifted all of these boxes to the left 1 unit. We've identified how that compares to the improper integral. And so now we can actually compute the improper integral. And just like before, we would have to take a limit. We'd have to take a limit as b goes to infinity of the integral from 1 to b, 1 over x squared dx, right? We know that becomes a negative x to the negative 1, evaluated from 1 to b. And then again, still taking a limit as b goes to infinity. So that will become a negative 1 over b minus a negative 1 over 1, taking a limit as b goes to infinity. And as b goes to infinity, the negative 1 over b disappears. So this ends up just becoming 0 plus 1. And so that entire red area was just equal to 1. So what does that mean? So the red area was equal to 1. That means that the series going from 2 to infinity, right? That's the original series minus the first term. So that series, except for the first term, must be less than 1. And then when we add in that first term again, when we throw in that first term, we get that the entire series must be, well, it could be bigger than 1, but it will be finite, right? It's something less than 1 plus one additional finite number. So we can ultimately conclude that this entire piece over here is less than 1, and this piece over here, at least, is finite. The smiley face. So that's our logical reasoning that lets us compare a converging improper integral to a converging series and vice versa. Okay, a lot of lecturing, another big pause. Let me know what you think so far. Any questions, any comments, any concerns? Okay, so I'm not hearing anything from you, so I am taking that to mean that so far so good. Let's jump down to the next slide. Well, this is, I guess, yeah, problem, hang on, scrolling. Yeah, let's just jump down to, let's jump to problem 5 and then we'll circle back around. Problem 5 is the final integral test that we want to talk about before we move on to some limit comparison tests and some regular comparison tests. So without actually drawing anything, let's just straight up use the integral test to show that this expression either converges or diverges, right? So what that would mean is I take the infinite series, 1 over n squared plus 1, sum as n goes from 1 to infinity, and I try to calculate, and I should say I compare it to compare to the integral from 1 to infinity of 1 over x squared plus 1 dx. Now, the conclusion that we're trying to draw, right? This is, I'll actually, do the annoying thing and keep my colors consistent. So what I'm really trying to do here is take this blue series and compare it to that red infinite improper integral. And I want to be able to draw a conclusion about one based on our conclusion about the other. In other words, I want to say that they either both converge or they both diverge. And I can do that assuming, go over here, I can say we can apply this integral test if and only if the following are true, right? So, and we'll see that this was true in all of our previous examples. So we can apply the integral test if and only if our function f of x is positive, f of x is greater than or equal to 0. Here, f of x is the expression 1 over x squared plus 1. Right, so we can apply the integral test if and only if that is true and f of x is decreasing. Right, we need our function to be strictly decreasing. Apologies, I know this looks terrible at the moment. I'll scroll back in a moment, but remember the fact that our function was decreasing is really what allowed us to say that these rectangles were definitely either overestimates or, if we shifted to the left, underestimates for the area. So it was the fact that the function was decreasing that let us say that the rectangles either hang over the function or sit under the function nicely. So we have to know that our function is decreasing to apply this integral test. So we want to check and see that our function f of x is in fact decreasing and is in fact positive. And it turns out both of those things are true, both of those things are great, right? F of x is positive. Yes, that is definitely true. That's because no matter what x value I plug in, x squared is going to be positive. Plus 1, that's going to be positive. And so my entire fraction is just 1 over a positive number, right? So our entire fraction here, 1 over x squared plus 1, is definitely positive. What about the fact that f of x is decreasing? How do we know that that's true? It turns out to be true, but we have to remember how we can check that. What do we check there? Anybody in the chat? I want to try to make this slightly more interactive lecture than just me talking to you. So anybody in the chat, what can we do to check and see that this function is actually decreasing? I love it. Yeah, so we got some answers here. Ooh, we got several answers. I love it. Okay, this is great. So Katie is saying the bottom is getting bigger. Alex is saying something similar. He's saying, look at the denominator. That's definitely true, right? Notice the numerator does not change. The denominator, as x increases, the denominator is getting smaller. And so, I'm sorry, back that up, try that again. As x increases, the denominator is getting bigger. And so the overall function is getting smaller. Yes, absolutely. Emma also has a great idea, and I want to highlight that as well. So yes, so we can see that this is decreasing because the denominator is growing. We can also take the derivative, as Emma is suggesting. And if we take the derivative, we can say, note that f prime, right? If we were to take the derivative of this, blast back to the Calc1 past, we have to use the product rule, the quotient rule. And the quotient rule would say that this is the bottom times the derivative of the top. So that's x squared plus 1 times 0 minus the top times the derivative of the bottom, all divided by the bottom squared. Right? And all I really care about is that as long as I'm plugging in positive x values, right, x values bigger than 1, this numerator is just a negative 2x, and the denominator is something squared. So what we get then is that this, whatever's under there, this becomes a negative numerator, a positive denominator. And so this derivative is actually negative. And since the derivative is negative, the overall function is decreasing, right? And so because the overall function is decreasing, yes, number 2 is satisfied. We can apply our integral test. And so what did the integral test say? Well, the integral test said that because those are satisfied, right? So since 1 and 2 are satisfied, what we have is that both the integral and the series itself will converge or will both diverge. So the sum and the integral will agree. Right? When I say agree, I mean they're either both converging or both diverging. So at this point, we just have to remember how to compute this infinite integral, which is itself sort of tricky. It's non-trivial, not easy at all, because we have to remember that that integral, first of all, is an improper integral. So let's do the proper thing. Let's take the limit as b goes to infinity of the integral from 1 to b of 1 over x squared plus 1. And then we have to remember what the antiderivative of 1 over x squared plus 1 is, right? And using our calc knowledge, or maybe our calc2 knowledge, we can point out that this is equal to the inverse tangent, right? So arc tangent of x evaluated from 1 to b, and then we take a limit as b goes to infinity. That's equal to, I'll say limit as b goes to infinity of arctan b minus arctan 1. And this is a little tricky. The arctangent of 1, well, let's remember, the arctangent of 1 is the angle for which tangent is equal to 1. And so that will ultimately be pi over 4. The tangent of pi over 4 is equal to 1. The limit as b goes to infinity of the arctangent function, that's a little bit trickier. So we actually have to remember, I'll draw this, pick a new color, draw this over here in our scratch paper. Our arctangent function, oops, right? Our arctangent function actually looks like this. It sort of looks like the tangent function laid on its side. And it actually has an asymptote as x goes to infinity, or as b goes to infinity. So as b goes to infinity, the arctangent of b gets closer and closer to a height of pi over 2. And so this should be pi over 2 minus pi over 4. The answer for that improper integral is actually pi over 4 then, and that's great, but all that I really care about is that it is finite, it converges. And so we can say that because this integral converges to a finite number, and because the integral test applies, this infinite series will absolutely, definitely converge as opposed to diverge. So that's maybe our most advanced example so far of the integral test in action. It involves both checking these expressions, right? So we have to check those expressions. We have to, when I say check those expressions, I should say check those conditions, make sure that the integral test applies. Then we have to actually compute the improper integral, determine whether it's finite or infinite, and then draw the right conclusion about the series as a result. So again, big pause, big sip of coffee. Any questions at the moment? All right, cool. So we've got about a half hour left in class, and what I would like to do is devote that time to the other big tests that we've talked about for class today, or in the videos, talked about in the videos for class today. And that was the comparison test and the limit comparison test. So let's clear that, and let's jump back to problems 2 and 3, right? Going a little out of order here, but let's look at problems 2 and 3. So as a reminder, the comparison test said that if you were able to compare one series to another series, so if you were able to construct a series A sub n and a series B sub n, and if A sub n as a term, right, every A sub n term was always less than or equal to every B sub n term, then if we know B sub n, the series B sub n converges, the series A sub n converges too. Right, and there were other implications as well. So if A sub n diverged, then B sub n would diverge. And I want to write that one up here as well. So if A sub n diverges, then B sub n diverges. Right, and the idea here was really the same as the integral test. It's really a question of comparing two areas. If our terms B sub n are always bigger than or equal to A sub n, then I know whatever this series is must be bigger than or equal to this series. It's just a matter of comparing what's possible. I should clarify that in this case, and in all of the cases that we're talking about today, all of our individual terms are themselves positive, or at least non-negative. So all of these terms are bigger than or equal to 0. So part of the comparisons that we're drawing come from the fact that I'm assuming A sub n and B sub n are both positive. What that means then, though, is that if B sub n is bigger than A sub n, this series will always be bigger than this series. And so if this is finite, then this would have to be finite as well. And conversely, if this was infinite, if this diverged, then this would have to diverge as well. So the comparison test, one of my favorites. We now have a small catalog of series that we know converge and series that we know diverge, right? We have our P series and we have our geometric series, and we have the harmonic series, which I guess is a kind of P series. So we can draw really nice conclusions by comparing our series, sort of stranger looking series or odder looking series, to the series that we know and love. And so what I want to do in these cases is try to draw some interesting comparisons. So let's compare this series to the series 1 over n, right? Let's try to compare 1 over n, the harmonic series, to this series here. And I have my question is, which of these series has larger terms? Well, if we think about it, right, just doing some algebra, 1 over n, that's equal to 2 divided by 2n. And that is actually going to be a little bit smaller than 2 divided by 2n minus 1. Right? As Katie and Alex said, we can compare the denominators in this case. right? So if we have 2n in this denominator, 2n minus 1 is slightly smaller, and that means that the overall fraction is slightly bigger. So in fact, we can compare these terms to the terms of the harmonic series, and we see that the harmonic series' terms are slightly smaller. And so what does that mean? Well, if I have this inequality, and I should have written it in the other order, right? I should have, just for aesthetic purposes, I should have written 2 divided by 2n minus 1 on this side. That's going to be bigger than 1 over n for each individual term. And what that means is that our series is actually going to be bigger than the harmonic series. Because the individual terms are bigger and all of these terms are bigger than 0, that means that our series on the left is going to be greater than the harmonic series. And since the harmonic series, right, since the series 1 over n diverges, one of our favorite surprising facts, since that diverges, the series 2 over 2n minus 1 will also diverge. Right? And how cool is that? So what we're really doing here is we're just taking a slightly more challenging looking series, right? So we're taking a series like this, and we are comparing it to a well-known series, a series that we know and love. And because we get the inequality in the correct order, we're saying that these terms are bigger than these terms, we're able to draw a big conclusion about this. So when we try to use the comparison test, this is often our strategy. I sort of look at my series, I sort of squint my eyes a little bit, and I think to myself, what does this series look like, right? What does this look like if it were a little bit simpler? How does it compare to series that I already know and that I already know and love? And so at that point, I could try to compare it directly to that series that I know and love. And then I just have to make sure that the inequality is in the right order, right? So if I'm trying to draw a conclusion, is it the correct conclusion to draw? Will it always be on the right side of the inequality to draw the conclusion that I want? Let's briefly talk through that example. Let's talk through the example down here. So using the comparison test, what can we say about the series 8 over 5k plus 30? And so again, I'll sort of squint my eyes and I'll think to myself, like, what exactly does this look like? Well, it has a constant up top, right? It has a constant number up top. It has an expression involving a k and another constant number down here. But it kind of looks like a c over k, or it kind of looks like a 1 over k. So this looks similar in structure to the harmonic series, right? In the sense that it has some extra constants that we have to deal with. It has that constant, it has this and this constant, but by and large, it looks very similar to the harmonic series. And so we know the harmonic series diverges, which means that if I want to draw a conclusion, my conclusion that I want to draw will be that this diverges. But in order to see whether or not this diverges, I need to compare 8 over 5k plus 30 to 1 over k, and I need to see whether or not I can make my inequality go in this direction, right? Because if I'm trying to say that this series diverges, I need to use this conclusion down here, which means that I need to be treating my harmonic series as my a sub n, which means that I need my terms of the harmonic series to be smaller than the series I'm actually looking at here. Whoops, sorry, there we go. Does that make sense? So what we're really trying to do here is when I'm drawing my comparison, I'm making a gut call as to whether I think this converges or diverges. And then I'm going to try to see whether or not the inequality works in the direction that I want it to. Okay. Oh, and I see I'm missing a 0 here. That should be plus 30, not just plus 3. So, yeah, thank you for that. Yeah, so at this point, what do we have to do? Well, we have to see whether or not this is true. And to do that, we can often try to manipulate. Well, let me see. What can we do? How can we explicitly show this? So the key, I think, is going to be similar to the observation that we made up here. Can I manipulate that denominator in such a way to get the correct inequality, right? Notice up here, the actual manipulation came in this step where I subtracted 1 from the denominator. And so in subtracting 1 from the denominator, what we can do, or maybe I should say what we did up here was we saw that we could actually, by subtracting 1, we got a larger fraction overall. That trick is not going to work down here, right? So if we try to manipulate this, what we're actually going to see is that we end up getting, if we try to do a similar thing, I could start with 1 over k. That's equal to 5 over 5k. But that will unfortunately be greater than 5 over 5k plus 30. Right? So by adding something to the denominator, what I'm actually doing here is I'm getting a smaller fraction. So I'm getting something here that's actually smaller than my harmonic series. And so unfortunately, I can't actually draw the conclusion that I want to draw. I wanted to show that this was true. Hang on, let me grab my spotlight. I wanted to show that this was true, but I'm not drawing that conclusion, right? I'm actually drawing a conclusion that looks like it's kind of going in the opposite direction. Kind of looks like it's going in this opposite direction. And so unfortunately, we run into algebra trouble and we say, because this, the 8 over 5k plus 30, appears to be smaller than 1 over k, it's unclear what conclusion we can draw. Associated sad face, right? It's unclear what conclusion we can draw at this point because the inequality isn't lining up the way that we want it to. I should say I'm sort of glossing over the fact that this was an 8 instead of a 5, but it turns out that ultimately that constant won't really make a difference. That particular constant won't make that much of a difference, right? To point out why that's true, I'll choose a different color here. Let's go green. We haven't gone green yet. To point out why that's true, just notice that because series are linear with respect to constants, right? I could pull that 8 outside of the entire thing and turn that into a 1. But if I then wanted to turn that into a 5, I could pull an extra 1/5 out and get this, right? So that constant in the top, the 8 versus the 5, ultimately didn't make that much of a difference. That's a total aside, but I just wanted to, just in case there were any questions about that, the real issue was this plus 30 in the denominator and how that wasn't lining up in the right direction that we wanted to, it to for the inequality. Okay, let me pause there and see, because I think these were some more advanced sort of questions. Are there any questions at the moment? Anything that I can address, either through voice or in the chat? Man, I am so happy I have a mute option so you don't have to like hear me slurping my coffee like up close and personal with the microphone. um, yeah, that's just a side thought. Great, so it looks like there aren't any questions at the moment. So what I wanna do, I'm gonna clear these drawings. What I wanna do, because I think I've been lecturing for quite a while and I want you to get some practice here. I want you to take a look at these two problems, problems 6 and 7, and if you finish them, going on to problems 8 and 9. Actually, let's focus on problem 6 and problem 8 for the moment. We have about 15 minutes. We have almost 20 minutes, but about 15 minutes left in class. I'm going to try to do this thing that we did last time. I'm going to break you out into some breakout rooms. I'm going to see how quickly and efficiently I can do that. And I am going to give you the opportunity to check in with each other, to chat with each other, and to practice some of these problems. And I will bounce from room to room, and with about 5 minutes left in class, I'll pull you all back to the center here, and we can talk through any issues that arose. So give me 30 seconds. I am going to break you up into some groups, and we can go from there. It's always just a little bit slower and more awkward, so I know you all are just staring at me while I do this. Give me a few seconds, though. I'll get this up and running just as quickly as I can. Okay, let's open these rooms and let's go. Okay, I'll see you in the breakout rooms.